Hi, my name is Professor Bill Buchanan, and I lead a podcast on the World Leaders in Cryptography series. I'm so happy to have Alfred Menezes here. Hi, Alfred.
Hello, thanks for having me.
And so Alfred is a professor at the University of Waterloo in Ontario, Canada. And in 2001, he won the Hall Medal within the Institute of Combinatorics and its applications. He is a lead author for the Handbook of Applied Cryptography, which I actually have here in my hands, and which has been cited over 25,000 times. He's published many high-impact research papers, especially in the areas of public key encryption and elliptic curve cryptography. He was also the co-inventor of the ECDSA signature method, which has taken over the world in terms of digital signatures. So, what's your current role and what does a typical day involve for you?
So I'm a professor, as you said, at the University of Waterloo. I've actually been on a half-time reduced workload since 2019, and I'm retiring next year. So, my days are much more relaxed than they used to be before 2019. So I spend less time in research than I used to. I spend more time learning things, which I enjoy, in cryptography, without the goal of necessarily producing new things. So I think I'm more in the learning stage of my career than my research stage. And I spend a lot of time on teaching as well.
That's good. Oh, it's nice to see that you're teaching. Certainly, it's an area that you can go on learning almost infinitely. There's always a new paper to read and a new method to investigate. So I think that's a great thing about cryptography. There's always something that you need to learn or possibly relearn again.
Yes,
So if we go right back, yeah, to your days at school, what were you like as a pupil at school?
So you mean as a child?
As a child, yeah.
Oh, yeah. So I guess mathematics came to me quite naturally. And I was lucky to have very good math teachers that were encouraging in all stages of my schooling system. My first few years of schooling were in the Indian school system in Kuwait, where I grew up, and then 6 years in an Irish Christian brother school in India.
Wow.
They have very good education and high math standards,
Wow.
followed by another 2 years in Kuwait, and then a year of schooling in Canada. And in all my years, I had very good math teachers that were very encouraging.
That's good. So I assume that's what sparked your interest in cryptography. What's the timeline between you learning maths and adopting cryptography as a subject?
Well, cryptography came in my undergrad at Waterloo, where I studied. Um, I was taking a course in coding theory from Scott Vanstone, who was also a professor here. And then in the summer, he hired me as a undergrad research student. Now, he didn't really have a good project for me, so it was more of a make work project. So I had a lot of free time. This was in 1986, to just at the library, going through the few books and journals I could find in the field. So I was reading all kinds of papers, at least the intros, and getting fascinated by the different areas within cryptography in 1986. So it was really a summer of independent reading by myself, getting paid to do it, mostly spent in the library, which sparked my interest in the subject.
That's amazing. And was that typically coding theory that you were looking at that time? Is that because the
The course
McLeese
was in
method?
coding theory, but Scott
Yeah,
had started doing research in cryptography. It was fairly new for him. So the summer
yeah,
was learning about cryptography on my own, mostly, which
yeah.
really sparked my interest in the field.
So 86 would be, so I think the RSA paper was 79, Diffie Hellman was about 76, 77. 86 would have been Shamir type work. Were you reading the papers of the time, or was it really just papers from the past and that you were reading at that time?
Papers from the past, but also the Koblitz and Miller papers
Mm.
on ECC were published in 1985.
It's amazing when you think that it goes back that long.
Yes.
Yeah.
And
Uh,
around 1985 is when Scott Vanstone had his interest sparked in ECC. And
yeah,
that was passed on to me in the summer of 86.
yeah. But few people actually picked up on ECC at the time, and I think it took 10, 20 years. It was almost like Satoshi Nakamoto picked it up for Bitcoin, and it took off. I mean, it was a slow burner of a paper. We'll come back
Yes.
to that paper, and obviously Neil Koblitz, the co-inventor of elliptic curve cryptography. So for your book, you cover so many areas. I must admit, when I'm on a flight anywhere, I grab my iPad and I open up the Handbook of Applied Cryptography, and I pick a chapter and I read it, and I get my pen out and I make notes and things like that. And it's wonderful because it's almost like the only time I get that actually is free time for me that I can really learn properly. So what's your favorite topic? You cover so many topics in that book. If you were to pick a chapter or an area, what is your favorite one?
So as a graduate student, I came from the mathematics side of things. So my interest was in the mathematics of public key cryptography, things like factoring discrete logarithms, elliptic curve discrete logarithms, and so on. And certainly at the time, I found most symmetric key things like hash functions, max schemes, terribly boring and uninteresting. Also, the theoretical aspects, things like multi-party computation, things I just never followed, never bothered learning at the time. When I started writing the handbook, though, since we wanted it to be a fairly comprehensive view of what was used at the time, that really forced me to learn things about symmetric encryption, hash functions, max schemes, and then I found them, somewhat interesting, because once you understand why something is actually useful and what the challenges are, then your interests are sparked. So over time, my interest within cryptography grew, but still, there were many areas I just totally ignored. For example, lattice-based cryptography, multi-party computation, because they were just newer areas which I didn't have time to get into. And as the years pass by, you lose a year behind the experts working in the fields. So you think it's too late to get into these subfields. But now, of course, my interest in lattice-based cryptography have been sparked. So I spent the last year learning quite a bit about it. And I'm also interested now in multi-party computation, because these things are being used in practice now at a remarkably fast rate. So over time, I've really had an interest in most areas of cryptography. So right now, there's nothing I would say I don't like anymore. So I like the mathematical aspects, the engineering aspects, the theoretical computer science aspects, and the implementation aspects, the deployment aspects. And that took several decades to broaden my interest to appreciate all these fields.
I completely agree. I've taken a similar route. I read Bruce Nyer. I talked to Bruce Nyer just yesterday, actually, and it was him that got me into public key encryption. I think it was Secrets and Lies book, and he wrote this chapter on public key encryption. I could really see the future and the power of it. That got me into it. I then learned the Diffie-Hellman method, and that just was like magic to me. And then the RSA method. And then when you start to lay that out, and the great thing is that these methods now need to be deprecated.
That's right.
For all our teaching for the last few decades have got to be stopped within the next 5 years or so. But the excitement is that Lattice is coming along, and Lattice isn't provably secure totally. So we need a backup, isogenies and multivariate cryptography. So I think you're right about that's one just little thing that's missing from your book is the lattice that I would love to have read about. But you're right, you could have went on to infinity and beyond. But I think you've got everything on the fundamentals there. I think finite fields is obviously a core thing. It's not a difficult thing, but it scares a lot of students overall.
That's right. One thing I should mention is when we wrote the handbook, we made cautious decisions not to include things which we thought might have potential, but weren't used in practice. So one big omission was elliptic curve cryptography, which was my main field of research, and also Scott Vanstone's the time the book was written. We didn't include it in the handbook because at that time, it wasn't clear whether people would actually use it in practice. So the book is lacking ECC, the handbook. And now it's also lacking lattice-based cryptography, but also ECC and pairings. So, it's just missing so many big things. It's really an outdated book.
Yeah. But you did write books about those things and research papers about those things. So the gap was there. But I think as a core fundamental read, I would recommend it to any researcher in this area to really learn the basic principles of things. And it's so easy to read, and it must have taken you so long to get all the maths correct overall in that. So it must have taken you years to get that. So you kind of gave a hint of your least favorite, but maybe you don't have a least favorite. Maybe you just like all the areas. Is there something in cryptography you don't quite like?
Also, since I teach applied cryptography for many years, I have to cover all the aspects with enthusiasm. This forced me to, for instance, if I present the AES block cipher, which is pretty dry, but I've learned to appreciate the nice things about it and emphasize the nice things in my classes. So even the things I found very dry and boring in the past, I've learned to appreciate a few things which are sort of interesting and exciting to me. So that's why it's hard to identify a sub area that I find boring or uninteresting right now, because especially lattice-based cryptography, which I consciously ignored for many years, now I find it fascinating.
Yeah, and I suppose it's all part of the patchwork. So there's no magic bullet there. You say this method will work here. You need them all to work together. That's how I like to teach it. I always say, we've not finished the story yet. Until we get to TLS and tunneling and so on, you won't see all these things working together, and they all have a place. There's public key encryption, but there's also HMAC. You choose between symmetric key signatures, or you have a public key. There's a place for both. And I think sometimes students are just looking for, tell me the answer. What is the one thing that I should know? But in cryptography, it all builds up together. And I think in AES, I like to say that you go through steps and then you go back the way. So it's like if you walk a certain way, certain directions, and you take your turns, all you're really doing on the other end is to go back the same walk. But everything you're doing is reverse of what. So if you multiply here, then you divide over there, and you take it back. So it is a beautiful method, and it's worked well. I think it's 20 years at least. But the Rindal, I feel sorry for the methods that didn't make it. That's what I feel sorry for. It's like NIST picks a method and it fossilizes. In hashing, obviously, the selected catcher, and now Blake 3 is so much faster than SHA-3. So I always feel sorry for the also rans in these things. Okay, so what topics do you teach? What's your syllabus? I know that you've published a lot of your material online now, which is great, and I highly recommend everyone to go and actually watch and listen to it. But what topics do you teach, and what's your methodology of teaching? Are you hands-on, practical, or theoretical? What's your approach for teaching your modules?
So we actually have 3 undergraduate courses in cryptography at my university. So one is the mathematics of public key cryptography. So that's focusing on the mathematical ingredients, including things like primality testing, factoring algorithms, discrete logs, pairings, and some security proofs. That's taught typically to a smaller class of about 20 to 30, mostly mathematics students. There's a theoretical cryptography course, which I don't teach, taught to a smaller class of computer science students interested in theory. But I've really, for 25 years, taught this course in applied cryptography. It's taught to now with 250 students at a time, but 2/3 of them are CS students, and the others are from the other branches of mathematics at my university. So it's taught, I teach it every winter to a very large class. And I'm normally I'm introverted. I don't like public speaking. I'm terrified of interviews like this one, but I somehow come out of my shell when I teach this large class,
Mm.
because I have a subject I know really well and
Mm.
is intrinsically interesting to students who are interested in applications.
Yeah.
So I get them motivated by the application. And once you do that, then you can throw a lot of math at them. And it goes down much better because they understand why the math is being used. So the course, I focus on the primitives. That's about 2/3 of the course, the little pieces. So I tell them why each piece is necessary, where it's used, the security definition, with 1 and 2 examples, and security properties. Then the last third of the course is on cryptographic deployments, where I show them how these things are used in large-scale applications that they all use in practice. So I cover, of course, TLS, which you have to in the cryptography course, but I also cover Bluetooth security, including the pairing process, Signal, the Signal protocol for messaging.
And
I
checking in things. Yeah.
explain how AWS does all their key management for everything they encrypt in their back end.
Mm-hmm.
I cover GSM security for cell phones.
Mm-hmm.
I think those are the main deployments of cryptography. So they get to see the primitives in the first 2/3. The last third is understanding how these things are used in very large scale applications.
Yeah. And I find when they're first exposed to some of the maths, and the maths isn't actually that difficult. It's logs, discrete logs, and so on, and a little bit of the RSA and the factorization and so on. But I think when they get it, it really makes a connection that something so simple is really the basis of their security. So I like to show maybe a browser and to say, do you know that you've got a key exchange in there? And it's basically Diffie-Hellman underneath. It's changed the elliptic curve, of course, but if it wasn't for that key, anybody could read your communications. And if it wasn't for that ECDSA or RSA signature, you wouldn't know if you were connecting. I find the most difficult topic and the least understood topic in cybersecurity is digital signatures. I don't know if you find this, but
in my class, I think I motivate the topics quite nicely, especially in doing symmetric key first, where they see the limitations and uses of HMAC, for example, of a MAC scheme. And so signatures, they see then what problem they solve that MAC schemes can't. And the best example is software upgrades. And when Microsoft broadcasts an updated piece of software to hundreds of millions of computers around the world, you need to be able to check the authenticity of the received piece of software. And you really can't do that with a MAC scheme. You can't have a shared key between Microsoft and all its users. So that's where public key is the only thing that works nicely.
Yeah.
And that's a very nice motivating example, which they get.
Yeah. And I suppose things like single sign-on tokens and things like that, that's where it hits the ground. If I use HMAC, it means that all of my clients have actually got to have my shared secret key. But if I use public key encryption, you have this magic. But you see many developers will go for these JWT tokens that are HMAC, and you go, are you really sure you want to do that? It just is easier to do it than with public key encryption. So I think that's where you're really trying to understand why you would pick this method over that method. That's obviously, and the great thing with cryptography and with TLS, you have a whole bag of cryptography that you can pick from, and it's a negotiated contract. And that's a good thing. You can deprecate things, you can move things out, and it all becomes very, very dynamic. So I like the way that things have really evolved in cryptography, where we've cracked things or the keys are too big now, but we can move them out and we can move these new things. And obviously post-quantum cryptography methods are starting to appear as part of the negotiation that we have. So I think you recently published a paper on the challenges of cryptography. Could you just outline what some of those challenges were?
Oh, yeah. So that was a paper really for the readership of the IEEE Security and Privacy magazine, which is intended for people who are not cryptographers. So it was a non-technical article on some of the big challenges with deploying cryptography on a large scale down the road. So one was standardization.
Mhm.
Right? So at some point, we need to be using the same in a small subset of cryptographic primitives for interoperability. TLS 1.3 was a great achievement because it really threw away a lot of the bad choices from previous standards and narrowed it down to a few things. So that was a great example of a grand success with standardization. Of course, the upcoming challenge will be standardizing post-quantum cryptography. NIST has a head start with the schemes it's standardized, but there will be challenges with other countries having their own preferences. Do you use hybrid cryptography or not will be an issue. And also, do you actually use post-quantum? Because it's not clear when quantum computers will ever be built. And the reason to use quantum safe schemes now is to protect against these harvest now decrypt later attacks, which aren't an issue for most applications, other than very high security applications. So standardization is important to drive deployment. So in the end, people will use things if they're standardized, whether they need to or not. So that was a big challenge. Another was key management. So my class, the first 2/3 are the technical pieces of cryptography, which in some sense are really well understood. But when you deploy this in a large scale, the real problems are managing a huge number of keys. And that's a problem which the problems aren't really technical. So cryptographers tend to spend less time on key management. But in practice, 98% of the challenges are with key management in large scale deployments. So that's something I like to drive through in my course, that in the end, in the real world, the big problems are with key management, not so much with technical cryptography, which the theoreticians and the academics do a good job of making secure. And the last suite of challenges was really advanced cryptography. The very broad field being privacy-enhancing technologies, which are really being used in a rapid pace these days, including fun topics like multi-party computation, which, as I said, for a few decades was really part of highly theoretical cryptography, which we could really ignore quite safely. But that's changed quite quickly in the last few years.
Yeah. Yeah, and it goes back to the 1980s. A lot of the theory, this Fiat-Shamir and things like that, I actually see that's taking 20, 30 years to actually get the zero knowledge, the privacy, the David Cham work and so on. It's taken all that amount of time, and really the distributed blockchain DLT stuff has really pushed. And I think if blockchain and DLT leaves a legacy in what it's actually been doing is it's pushed the envelope because it had to in all of these areas. And when you talk about post-quantum cryptography and TLS 1.3, TLS 1.3 deprecates or doesn't deprecate, it erases the RSA encrypted key, to use public key to pass the key, and we just end up with a Diffie-Hellman or the elliptic curve Diffie-Hellman method now because of the long-term security of the server losing its private key and revealing all the keys from the past. But post-quantum cryptography doesn't support Diffie-Hellman anymore, although the isogenies did it, but they got cracked. And NIST really wanted isogenies to win, but it didn't with Cyc. But now we have key encapsulation, KEM. So I think Kyber is now called a really boring name. I don't know why NIST made it so boring, because I liked Kyber. Crystal's Kyber sounded like Star Trek or something like that. And now they give it the boring name.
There might be some related trademark issues, I believe.
There definitely would be for that. But they call the ML hyphen KEM FIPS 203, and it's so boring.
I still call it Kyber on dilithium. It's much more interesting.
So do I. Dilithium. So dilithium, they've not given Vulcan a name yet, but obviously you've got dilithium, which is it MLDSA?
That's correct.
And then the other one I never remember. This Sphinx
ML
Plus. ML Kim, that's right. And they've given it such boring names, and I think they should have given them much more interesting names that they had. So you're interested in elliptic curves. I'm interested in elliptic curves and elliptic curve cryptography. I mean, obviously, elliptic curves are a big area of mathematics, and it's
Mhm.
quite difficult to find points on an elliptic curve and so on with its pure. And then we bring in this magical mod p, and then all the points appear almost like a big random thing. It's always strange when you're teaching elliptic curves. I don't know how you teach them, but I just teach them like the analog. This is an elliptic curve, and this is the mathematical equation. And by the way, it's got mod p, and here's what it looks like. But don't spend too long here. But there's lots of points, and every point when you add another point, and so on. So, what got you into elliptic curves and elliptic curve cryptography?
It was really my advisor at the time, Scott Vanstone. He attended Neil Koblitz's talk on the topic at Crypto 85, and he was intrigued by elliptic curves. So he started a reading group at the university in 1986 when I was an undergraduate student. So really the enthusiasm came from Scott Vanstone, who was influenced by Neil Koblitz.
Yeah, yeah, that's and you wrote the paper on ECDSA. So Kravitz created DSA, and I think he created
Mhm.
this patent that assigned it to the US. Good on him, well done. Uh,
Mhm.
and then that basic methodology of the discrete logs was then converted into elliptic curves. Did you know at the time that this would be so powerful, or was it just another paper for you? You just thought, I'm writing something that just takes something on a little bit more?
So the paper actually came many years after we had
Mm,
standardized
mm,
ECDSA. So the background is around the mid early 1990s, Scott Vanson had a company, Certicom, which was
mm,
promoting elliptic curve cryptography.
mm,
So he was trying to get it standardized. So I worked as a consultant for the company, attending standards meetings by the IEEE and ANSI. So my job was to introduce elliptic curve cryptography to the standards committees. And there was a lot of resistance to the new technology because they didn't know what it was and they didn't understand it and they didn't know why it would be needed over RSA because RSA did a good job. And so we tried proposing our own signature scheme. Then we discovered to make elliptic curves more appealing to the standards committees, it would be easier to mimic the DSA, which they understood, as closely as possible to get something that looked very much like it, which they then would more willingly accept. So we really tried to modify DSA in as few ways as possible and came up with the ECDSA.
yeah,
In hindsight, ECDSA is not the nicest signature scheme.
mm,
Ideally, we would have started with Schnorr, which
mm,
is nicer than DSA, then modify Schnorr to get EC Schnorr.
yeah,
But DSA was standardized first because Schnorr was patented. And the US
yeah,
government wanted to avoid the US patent on Schnorr. So they came
mm.
up with DSA. And so we mimic it to get the ECDSA. Then once the standards were written, we wrote a paper on it, which was a few years later.
That's amazing. And I mean, I think the Snore signature was held back, and it's only just recently that EDSA
That's
is
right.
now a FIPS standard by and it can be used in finance and so on. And it scales very well. You can do the
Mhm.
Shamir share, and you can do distributed signatures easily. And
That's right.
researchers are still working on trying to. It seems that they come up with methods. I think Frost was one, and so on that had this multi communication of the ECDSA share,
Mhm.
but it gets cracked and things like that. So we're really struggling. But ECDSA is king of the hill just now. I mean, for anything in blockchain and Ethereum, it's ECDSA.
Yeah, in blockchain, really because Satoshi Nakamoto,
Yeah,
when he designed Bitcoin, made the choice to use ECDSA.
yeah.
In hindsight, he
Indeed.
should have used EDDSA or a Schnorr variant. Would
Yeah,
have been a bit nicer for many of the cool applications of blockchain. But both Ethereum and Bitcoin made the early decision to use ECDSA. So
yeah,
the blockchain community was kind of stuck with those things.
yeah. And he used sept 256 K1, not R1, which is the one that we
That's
typically
right.
use these days. So I think it's x squared is equal to x cubed plus 7 mod
That's right.
p is what he chose. It's not a guarantee because I don't think we know the seed value that was used to generate the curve as far as I can tell. So there is still some worry that the NSA can crack that curve. I think curve 25519 is more secure and more provable in that.
Yes, I've written on this topic, and to me, it's very far-fetched that NSA would have any kind of a backdoor on the elliptic curves that's standardized, and for many reasons. One being, NSA would, in the mid-1990s, have known of an attack on these specific elliptic curves, which it's been 30 years and the rest of the world hasn't found as yet.
Yeah.
So if you think the NSA has that much advanced mathematical capability over the rest of the world, surely you must then conclude that by now they can break all of ECC, not just specific elliptic curves.
Yeah. I,
So,
I agree completely. Yeah. I mean, I think they've
and the
generally.
fact that they standardize these curves to be used
Yeah.
by the US government,
Yeah.
and I don't see, if they could break them, I don't see how they could expect that other governments, whether it be China or Russia, they have strong teams working for them too, wouldn't discover the attacks in the ensuing years.
Yeah.
So the NSA has a very strong record of choosing things which are secure when they recommend them for US government.
Yeah.
The exceptions are DES, which had very small keys, but at the time, the keys were long enough for most applications, while small enough for the NSA to do exhaustive key search on.
Yeah.
And the other exception is the trapdoor they had in the elliptic curve pseudorandom bit generator. Yeah, but
right.
from their point of view, that was a good trapdoor, because a trapdoor was finding a discrete logarithm, which presumably only they knew because they picked the logarithm first, and no one else could find. So, I'm not in favor of trapdoors, but if you're going to put one in, make sure it's a trapdoor which no one else can ever find.
That's right. Yeah. Yeah. And we see the brain pool curves coming along, and I think they are cleaner, but nobody uses them because we're stuck with these P256. If it's not NIST and it's not FIPS, then it's not acceptable. If it's not the EVM, Bitcoin curve and Ethereum, then it's nowhere. So is it likely that elliptic curve will fall before RSA? Because I hear a lot of people saying we're just going to ramp up the RSA key size.
There's been no advances in factoring since 1990. And the last advance in elliptic curve discrete logarithms for elliptic curves over mod P fields was also around 1996. So it's been about 30 years before we haven't seen any advances in classical attacks on RSA or ECC. So it's impossible to predict the future. I mean, anything could happen. We have no reason to expect anything will break before the other thing.
Yeah.
Of course, they both break. They both fall to attacks by quantum computers. But ignoring those, we have no way of predicting whether RSA or ECC will fall before the other, if indeed any of them falls to an attack.
Yeah. Because RSA is still the most widely used public key signing method. If you look at most of the certificates that you find, so ECDSA is making inroads for that, but RSA is still, after all these years, still the most popular signing method. And it'll take a lot to push it off. And I really worry that banks, critical national infrastructure will have to go. And I know in the US, there is this mandate from the NSA and so on to actually get rid of all public key encryption methods within critical national infrastructure, which is education, healthcare, and energy, and so on. So I think the US is probably driving the field much more. The EU probably needs to catch up. I don't know where Canada is. You would generally does Canada generally follow the US and in its standards?
Yes. As does the UK, New Zealand, and Australia for
Five
classified
Eyes.
applications.
Yeah, 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 yeah. For us, it'll be the GCHQ and the NCSE that will
Yes.
probably start to mandate it across. And I think it'll happen in a year or two,
Mhm.
because obviously I think NIST have defined this 5 year window of deprecation for any
Mhm.
contracts that are awarded. I think you will have to show that you have post-quantum cryptography methods, hybrid, as you say, possibly. But then
Yeah.
even the hybrids will get switched off
Yes.
eventually after 5 years.
So just last week, I think NIST announced their draft timeline for deprecating RSA and ECC, and it was 2035,
2035,
only
yeah,
11
that's
years
right.
from now. Of
Yeah,
course, that one happened everywhere. It's just impossible.
yeah. And
We still have MD5 used in many, many,
yeah,
many places.
that's right. And
You can
especially
still
in law
find five
enforcement.
12-bit RSA keys in applications,
That's right.
so it'll never be eliminated, but it's happening. The transition is happening much faster than I would have predicted even a year
Yeah,
ago.
yeah. Because 3DES is 112 bit. As you said, DES was the 56. We do this
That's right.
3 with two keys to 112, and we need to move to 128 at least, and then 256. But I
Mhm.
think NIST said that all 3DES should finish December of last year. But I'm fairly sure my credit card will probably still be using DES. And I know that AWS has a platform that does 3DES encryption still. So it'll take a while for
That's right.
3DES to leave the stage. But it's still strong. I mean, the Lucifer cipher that was created by Forrest Heistel is still uncrackable. It's a beautiful cipher. I don't know if you show that one. I'd love to teach that one where you do the intertwining
I used
of
to, but I
the
pulled it out just because of a lack of time in my
yeah,
class. It's a 12-week
yeah,
class, and I, want to get to the things used in practice. So I've
yeah,
taken away things like triple des over the years.
yeah,
I
yeah.
took away discrete logs 5 years ago.
Ah,
So when I
yeah.
do
Not to
Diffie-Hellman,
teach
elliptic
Diffie-Hellman.
curves, I go straight to
Yeah.
elliptic curves.
Oh wow. Wow,
So no
that's
more,
interesting.
and it's actually a bit easier because when you
Yeah,
do mod P Diffie-Hellman,
yeah,
you really need to be working with an element of prime order.
yeah, yeah,
So you've got to define order of an element, and that takes
yeah.
a whole lecture with
That's right.
notions from group theory,
Yeah,
which I can completely skip when I get to elliptic curves. I just use elliptic curve over a
yeah,
prime field with a prime number of points. And I just tell
yeah,
them that the points can be arranged in the cycle, and I'm done.
yeah.
I actually save a bit
That's
of time not doing mod P discrete logs in my course.
That's interesting because you've got the generator value and you've got to make sure the generator value works for the prime
That's
number
right.
that you have. And in real life, you pick the prime number first and then
That's right.
you pick the G and
The
then you
order
make sure
first.
the P will work from there.
That's right.
That's really interesting that you take that approach because you do need to get to ECDSA because that's the only show in town. There's nothing else anymore
Yes.
with TLS 1.3.
And also
So,
ECDH is what's used most widely.
yeah,
So like
yeah,
Bluetooth, when you pair to Bluetooth devices,
yeah,
what's happening is an ECDH key exchange using P256.
yeah. And I mean, there's going to be problems because I think Kyber is looking at 500 bytes, 700 bytes, and so on. And eventually it doesn't fit into a TLS packet. So there's going
Yes.
to be quite a bit of overhead. And we've been lucky with the ECDSA, the small public values that are actually passed. So, and I know that maybe TLS is a terrible, TCP/IP is a very terrible stack. And probably this will force the industry to move away from these small packets that we send, small segments, towards something a bit bigger. I think when you get to Sphinx Plus, you're looking at 16K or something like that for a signature size. That's a lot of
Mhm.
packets that you're going to have to send. So I think that's going to be the thing that will have to be assessed. The latency, number of packets, the overhead in TLS is going to be the biggest overhead, I think. So you worked with Neil Kobolitz, who was the co-inventor of elliptic curve cryptography. As you said, that paper was written a long time ago before it was even picked up. I think it might have been, yeah, I think it was around the Satoshi Nakamoto's time that it really started to pick up. When you look at the Google Scholar, it's a low burner, and then all of a sudden it just goes up around 2005 or so was when it was really getting picked up. So when you read the original paper that he wrote, did you see the potential of it?
To be honest, no. I was at the time, an undergrad student.
Mm.
So really my inspiration came from my advisor, Scott Vanstone.
Mm.
So he was excited by Neil's talk in '85 and saw the commercial potential of elliptic curves as well. And so really my enthusiasm came from Scott Vanstone. Over time, I developed my own opinions, but it took a few years to get there. Initially, it was really Scott Vanstone's inspiration.
Yeah. I mean, I don't think anybody really did. Maybe even Neil himself didn't really. I can't remember what he said when I asked him about this. But
I can tell you. So Neil at the
yeah,
time was a postdoc. I was visiting Moscow, and he
yeah,
had to
that's
give a
right. In
talk
Vietnam
to
and
he had to give a talk to
places
these
like
very
that.
eminent mathematicians, and he didn't have much to talk about. So he basically just thought about using elliptic curves the night before and gave a talk on that. And Neil is anti-capitalist today, till
Yeah,
today.
yeah, 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 yeah,
He did
yeah.
not invent them
No,
with any thought of applying them in practice or making money of them. Not even close.
it's true. Yeah, yeah. He could have made like the RSA patent was worth a fortune. I mean, they had to create a company. The
Yes.
patent was there to protect, and I think MIT uh, protected the patent, and then they allowed the company to happen. And obviously, the Diffie-Hellman method. I talked to Marty Hellman, and he said he didn't make a lot of money from the
Mm.
patent because Stanford were a bit more open. They didn't spin out a company with the method, but the RSA and Neil could have made billions for every connection that happens on the internet. He could have cleaned up on that.
Neil's anti-capitalist, so doesn't
Yeah,
wouldn't.
that's it. Yeah, I've read his book, and it's really interesting where he goes to Vietnam, and
Oh, yes.
I think he talks about the Vietnamese ciphers and things like that, and he visited Russia and so on. Really interesting. Only in Canada. Only in Canada.
But Neil is American. He's at the University
Yeah,
of Washington in
yeah, that's
Seattle.
right. Yeah, yeah. So the original, yeah. So the original paper was in 1957, and it took a long time for it to be adopted. And you think it was the Bitcoin advancement that really took off? Was there anything else that really pushed
I
it?
think the Bitcoin was more getting ECDSA, you know,
Mm,
known to masses of people. But the
mm,
first standards were published in, I think around 1998, 2000. The FIPS came out in 2000, I believe. So really the NIST FIPS on ECDSA was the first formal stamp of approval of ECDSA.
yeah,
And that's when it started getting deployed in commercial applications before cryptocurrencies even.
mm, yeah. So how do you teach uh, elliptic curve cryptography? I mean, there's many methods of doing. How would you explain to the general public how elliptic curve cryptography works?
So in my course, which you mentioned is now online, I do really 5 lectures. The first is the basic mathematics, showing them what an elliptic curve is, the equation,
Mm,
and the addition rule. The second then introduces the discrete log problem, just defining the
mm,
problem and
mm,
explaining the fastest attacks known in the problem, of which baby step, giant step can be really explained to a fairly new audience. And that is essentially the fastest attack known.
mm,
And then I move on to ECDH, which is
mm.
conceptually very simple, and ECDSA, which just has a slightly complicated signing
Yeah,
equation, but beyond that, it's also conceptually quite simple. So it really works quite well in about 5 1-hour lectures to
yeah.
my undergrad students.
And so did you find the parameters, the A, the B, the P, the G, the base points? So you've got little g, is the base generator and discrete logs, and then you've got the big G, which is a base point on the curve, and then you've got the order. I always find that's the sticky one because the order is the one that's really important, because when you're doing your calculations, it's often mod n, not mod p,
That's
and
right.
it's trying
Yes.
trying to explain that the n is actually the order. Is
Yes.
you can't get all the points on the curve, but you can get
Mhm.
most of them, hopefully, if it's well designed. But the order is the magical little thing, and that
Mhm.
is where you get the security. So
That's
it
right.
isn't 256-bit security, even though you're using this prime. It's the order size that gives you the core of it.
Mhm.
And I think that's really important. And obviously in group theory, the order is really important. In discrete logs, the order is equal to p minus 1. That's
That's
fine.
right.
But elliptic curves, it kind of changes it there. So that's often a difficult thing to get over. And I don't think many people quite understand the importance of n in a curve. So you've written many papers with Neil, and I think you wrote a series of papers with him on the website anotherlook.ca. What was the focus of those papers?
So yeah, Neil and I, we both come from the mathematical side of things. And in cryptography, there's mathematicians, there's engineers, there's computer scientists. And the computer scientists, I'm speaking very broadly, they tend to focus more on designing useful things one can do with hard problems. The mathematicians study the hard problems and why they're hard. The computer scientists assume the problem is hard and they want to use it to do something useful, whether it's signatures, identity-based encryption, really cool stuff. But more importantly, prove that the schemes they design are secure, assuming the underlying problem is hard. And that's the area of provable security. In any cryptography conference, most presentations are about new protocols, new schemes, and proving that they're secure. So this segment of the community view security proofs as what makes cryptography a scientific field. In other words, without a proof, what you've designed has no basis in science. Yeah, which is a fair statement, except it turns out many of the proofs have sometimes very little, sometimes even no practical relevance. So while proofs are nice to have, you should know whether the proofs you have are useful in practice or not. So we wrote the series of papers to bring attention to the fact that many proofs in the community, in the field, are really nice, of course, and good to have in a sense, but sometimes of very limited relevance to practice. And these things were maybe known to most people in the field, but it's usually never written down in any prominent way. So you might find the odd mention here or there, but never, in the abstract of a paper. It may be buried in the last line. So we wrote a series of papers explaining the many ways in which proofs can be meaningless in practice. And
Yeah.
that was a rather controversial series of papers, I might add. Which of course is why Neil liked working on it, because Neil loves controversy, being someone he just always liked controversy.
That's really interesting, and it's true. I mean, if I can design a system and I have four boxes in it, and I say that's secure, that's secure, that's secure, and that's secure, then I can now say, hopefully, that the whole thing is secure. So it's making those assumptions that the discrete log problem tick, but
Yes.
it's not definite. It's just a hard problem at the current time. But if something happens with this discrete log problem, such as quantum computers, then that's a cross and it's
Sure.
not provable anymore. And I think it's
So
a
that would
big
be fair,
challenge.
except you also need to define what you mean by security.
Yeah,
And it's hard to
yeah,
get right. So typically, a researcher will make a definition, design a protocol, and prove it's secure with respect to the definition.
yeah,
But then they discover next year that the definition doesn't cover all attacks that you might care about in practice.
yeah,
So you have proof for security against a limited set of attacks, but you've omitted many maybe realistic attacks, things like side channel attacks, which typically are not covered by security definitions. Also, sometimes, you can't prove your scheme secure with respect to a natural problem like discrete logs. So often the researchers will modify the problem to something much more exotic and not well studied. They still have a proof, but with respect to a problem that is no longer a well-studied problem.
Mm.
So
Yeah.
there are many ways in which proofs are mathematically correct, but can be quite meaningless or a very, very limited use in practice.
Yeah. And I suppose it comes down to a dollar value that you put down a dollar value. This is how much it's going to cost me. It's like the 50% attack on Bitcoin. How much will it cost me to get the consensus on that? Because if I can make it too expensive, then it's too expensive for you. So I suppose it's not bits that it comes down to. It's actually dollars, the amount of dollars it will take me to crack this, and how long will it actually take me. I like the paper from I forget the author just now, but he not Dijkstra. It was a paper that outlined how much energy it took to crack each of the symmetric key, public key, and hashing methods.
I see.
And I think something like a teaspoon of water boiled would be the cost of cracking, I don't know, 30-bit hash and so on. You go up to 128-bit, and you would have to boil all the oceans on the planet to crack 128-bit symmetric key method. And that's actually true. So many people think, oh, 128 isn't secure enough. It is. To crack with brute force, 128 would take you so much energy. But obviously quantum computers will change that. So he looked at actually defining the amount of energy that would take to crack these things. And I think it puts it into context what security really means, that everything is crackable, but it's just the amount of cost and time it would take to crack them.
I think that's a paper by Arjen Lenstra and co-author.
That's exactly right. Yeah, I knew the paper, and I've just forgot the author there. But it's a really great paper, and he's created so many other great pieces of research work. So obviously, ECDSA has its problems. I mean, I think there's nonce reuse. You've got to make sure you destroy the nonce. You've got to make sure that the nonce doesn't repeat, and so on. So it's got to be treated with. And I think there was an attack on the PlayStation operating system at one time where they had the secret key of 9. I'm fairly sure that's the case. Someone picked a secret key of 9, which I suppose is a random number, you could say. So I think sometimes it's not implemented that right. But you discovered an attack called the MOV attack on elliptic curves. Could you just outline how that works?
Yes, that was an attack on a very special class of elliptic curves, which were actually described in the original papers by Kolbitz and by Victor Miller, because they were easier equations to write down and to count the number of points on them. So it was an attack that moved the discrete log problem from elliptic curves to finite fields, where faster attacks are known. And it used something called the Weil pairing and the Tate pairing, something known to mathematicians for many decades. Anyway, the nice thing is, when we found the attack, the first reaction of some people was that elliptic curve cryptography was all broken. When in fact it wasn't. There was just a very small class of curves that was found to be less secure than before. You could easily avoid those curves in practice.
Yeah.
But then in 2000, when pairing-based cryptography became a thing with identity-based encryption, and now with zero-knowledge snarks in blockchains, well, the mathematical piece they need are precisely the elliptic curves which we broke in the 80s. Because you want the pairing to be effective. And so the curves used in all the blockchain applications with zero-knowledge snarks are the ones we broke in 1990. So they were resurrected, many years later, from being insecure to being really secure and useful in practice.
with pairing-based cryptography, that is real magic. And it's, I think if someone can master pairing-based cryptography, they can write so many research papers. But it's a really difficult topic to explain, these
Oh,
two
it's
curves.
only difficult if you want to understand how the pairing is actually constructed.
Yeah.
But if you accept that as a black box,
Mm.
it's really quite simple.
Yeah.
It's a Diffie-Hellman with three parties and exponents move around magically is a high-level overview.
Yeah.
But you can really explain, if you understand Diffie-Hellman, you can understand pairing-based cryptography.
Yeah. And I think obviously with the post-quantum cryptography, we're still struggling to find a replacement for these things. So there is a Shamir equivalent in post-quantum cryptography in the lattice now, but I think a lot of the primitives, we're struggling to find the equivalents, and I think that will be one of the big challenges, obviously, that we'll have. And so the Maclise code-based method has been around for a long, long time. Obviously, he's dearly departed now recently, and it's still got a chance. I think the round two or the next stage of the key exchange after Kyber, because there's only one method that's been approved just now. Uh, Maclise, Bike, and HQC are the three methods.
Mhm.
So do you still think there's what is it that makes code-based cryptography so strong for its security guarantees?
Um, so what's really in its favor is that the code-based schemes were designed in the 70s. So they're 50 years old now, much older than lattice-based systems.
Mm,
So some would argue, especially Dan Bernstein, that
mm,
the McLeish-based schemes, if the codes are carefully chosen,
mm,
are perhaps more, you have a better guarantee of security than lattice-based systems. The problem, though, is with code-based encryption schemes are the massive public keys.
mm,
They're just massive compared to
yeah,
lattice-based public keys.
mm,
So, they might find some niche applications, but, my feeling is that given the head start that Kyber and dilithium have on the other schemes, it'll be very hard to, in 3 or 4 years, replace them with a code-based scheme.
yeah. And obviously the key generation is seconds, so you're not going to be using it in a TLS key exchange anytime soon. So I think there is maybe it's like Sphinx. If you want really concrete signatures that are going to last for decades and so on,
Mhm.
then just stick that on it. So maybe Maclise is something that would have its niche in certain applications that needed to be secure for 50 years or so, or if someone didn't try trust the lattice methods. So in your book, one of my favorite chapters in this book is where you cover the patents. I think that's a great because it gives a landscape of what happened when and who did what. Because typically these methods they were published. I think the Diffie-Hellman paper was published first, and then the patent came after it. I don't know how they
Mhm.
managed that. I know there's a year in the US or something
In
that
the
you can,
US. Yeah.
even though you tell people about it, you can then patent it. And I think the RSA method was published in Scientific American, and
Mhm.
they went and sent all these papers out across the world, and the NSA tried to stop that, but I think MIT had already sent the papers out. So I like that chapter, and you've split it up into the different generations. So the 1950s to 1970s, you talk about the Horst Feistel cipher and IBM, Lucifer, and Lloyd's Bank in the UK adopted it, and so on. There's the Diffie-Hellman method patent, and then RSA, and then you then go on to the 1980s, which is starting to look more like the David Cham privacy-aware things, the Snore signatures, Fiat Shamir, and the Kravitz signature for DSA, and so on. So, out of all the patents, which one do you think really made the most impact? What's your favorite patent of those?
Well, I guess impact from an academic point of view, we sort of hated patents.
Yeah, we did.
But
Yeah,
certainly the ones we hated most were the RSA patent
yeah,
and the Diffie-Hellman patent,
mhm,
because the Diffie-Hellman patent had claims against for all public key cryptography, not just Diffie-Hellman. So in principle, even if you wanted to use RSA, you had to license the Diffie-Hellman patent as well. So it was very broad claims in the patent. So from a purely academic point of view, their patents are horrible. And from a commercial point of view, if your goal is to make money, they can be very useful, but they can also slow down the deployment of technology by many years as well.
yeah, yeah, yeah. That's true. And yeah, that's it's interesting that you say that because I think it was Whitfield Diffie who did the concept of public key encryption in the paper, but it was Marty Hellman. I've actually seen Marty Hellman's desk. Every time we speak to him, he shows the desk in
Oh, I see.
Stanford where he actually did the maths. So I think the two of them worked together as a team. Whitfield was very much the dreamer and looking forward, where Marty was the mathematician and the concrete. Just like the RSA team, Revest was a kind of thinker.
Mhm.
The Shamir was very much a cracker, so he would
Right.
crack methods like the Merkel method, Hellman method. He cracked, and then Edelman was very much the theoretician who would take reverse ideas, and Shamir and Edelman would crack them. And it was only when he had this one brainwave that they found that they couldn't actually crack it, and it was a good method. So, what is it between you and Neil that makes you such a good team together?
Oh, good question. So Neil's a few years older than me. So Neil, of course, is a very good mathematician. He has, very strong foundations in math. He's a very smart person,
Yeah,
but he has many interests outside mathematics. He has political interests, and he
yeah,
spends a great deal of time, and he's been very effective in some ways in countries around the world. Um, so to answer your question, the way we usually work is I visit him with a fairly vague idea to write an article on something, but my ideas tend to be half baked and a little jumbled, and I'm a little bit confused. So my main first step is to get Neil interested in what I'm thinking about. That takes a while because
yeah,
Neil doesn't want to learn things that seem messy and jumbled. But once he sees the idea, you know, then he works very quickly. It takes me a while to keep up with him then. He's also a very good writer, so I benefit from his very great writing skills. But I don't know why we work well together. We just do.
yeah, yeah. That's amazing. So, what do you think the next decade of cryptography looks like? What are the key problems that need to be solved?
So certainly now it's post-quantum is
Mm,
uh, standardizing post-quantum, deploying it widely. And as you said, trying to find lattice-based equivalents
mm,
to all the protocols, used in blockchain, for instance, the cool stuff, beyond just signatures and encryption. So that'll be a lot of work in the next few years is making quantum safe analogs of the really advanced cryptography we want to use in practice. The other is things like the broad topic is privacy enhancing technologies,
mm,
including things like privacy preserving machine learning. So bringing the cool cryptographic techniques for multi-party computation to large scale machine learning, is a really fascinating challenge.
yeah, I completely agree. I think machine learning is struggling just now with privacy and so on. I think the homomorphic encryption will actually allow us to feed in to create public models of machine learning and feed in encrypted data like fraud data and so
That's
on,
right.
personal medical data. You could feed into a machine learning model, get a result back, and then decrypt that with the private key. I think that is a winner. But we need to get the chips and the GPUs and the edge computing in place for that to happen. I think Apple are doing it Certainly,
That's right.
Apple are starting to use homomorphic encryption, and they have a nice secure cloud that they have for this processing. So that is generally, I think, the way that the industry needs to go. So, if you were to change one thing about your career, I probably think that you wouldn't change one thing. What would it have been?
Nothing major, because to be honest, I think I've been very lucky. I don't consider myself to be a really smart researcher type person with incredible talents. I just was always in the right place at the right time. Just something small would be, cryptography changes over time. I wish I could have taken all these courses that I need now during my undergrad and grad studies. But of course, you never know what kinds of mathematics or computer science or engineering one might need in the next 10 years. So, for instance, I wish I could have learned more algebraic number theory in my early years, because that came up in so many areas of cryptography, including now lattice-based cryptography. So, yeah, so in hindsight, I would love to go back in time and spend my years learning the math I would need 10 to 20 years later. But of course, that's
I,
impossible.
I completely agree. I mean, I had to go and relearn all these things. I moved from engineering into, I did data comms and encoding theory and all that kind of thing. And then I moved into a computer science department, and I was
Mm-hmm.
quite surprised that there wasn't as much mathematics as there was in engineering. And for a few years, I didn't do the maths, and I just felt that there wasn't something quite right about the papers that I was publishing. They didn't have a concrete foundation in what
I
they were
see.
actually doing. And I got back to maths and I started to relearn the principles. And it worries me that sometimes that the undergraduates and postgraduates aren't learning the core maths.
That's
They're
right.
just jumping ahead.
That's right.
I don't have to learn polynomials and these kind of things
Mm-hmm.
anymore. I'll just use lattice cryptography, and who cares? And that would be a really sad world that we move to, that we rely on
Yes.
ChatGPT for all our maths principles and things like that. So, what advice would you give to graduates who were nearing graduation in this area, like digital trust and cybersecurity and the kind of
You mean
tech
undergraduate
areas?
students?
And undergraduate, postgraduate, what kind of skills would they need to pick up? What kind of knowledge would you advise them to make sure that they had to go into industry?
Yeah, so for undergrads, I tell them, don't spend a lot of time learning cybersecurity or cryptography. Take a couple of courses and that's enough.
Mm.
Spend your time getting a good foundation in mathematics, computer science, and engineering,
Mm.
if relevant, because the field is changing and you have no idea what you might need once you get a job, for instance, or if you go to graduate school. So build the foundations and only take one or two courses that are specialized to make sure you enjoy the material. Of
Yeah.
course, once you get to graduate school, if you get there, then you want to specialize. Then you pick your research fields more carefully. But as an undergrad student, build the foundations.
I think that's fantastic advice, and I see that completely. Undergraduate, you want to be understanding all of the core areas because you don't know quite what you're going to do. But for
That's right.
postgraduate and for PhD, then focus and become that expert on the thing that you actually want to learn. So if you were a new researcher just now, what problem would you work on?
I would love to get into multi-party computation. Um, I'm still really new to the field. I've been learning the basics. There are really nice, highly theoretical questions in the field, but also now you can write many papers on applications, just like in machine learning. A small part of machine learning is the theoretical foundations. A larger part is new algorithms, but the biggest piece is just cool applications where you just pick a new application domain, apply known techniques, and get cool results. Multi-party computation is sort of like that now. And there's hardcore theory, cooler algorithms, and then really cool applications. And so you can focus on really difficult theoretical questions, more algorithmic questions, or very practical questions. So there's a wide range of problems you can interest grad students in this formally very theoretical field. So I would love to work in multi-party computation where I just start over again.
And provable security and things like that. I think you've worked in all the great areas anyway, and you understand all the core theories that are around. So thank you very much, Alfred. That's been a really enjoyable hour and a bit chatting with you. I think we've just scratched the surface on that mighty brain of yours and the work that you've actually done. So thanks so much for spending the time. I know it's a busy time for you, and all the best for your retirement when it actually happens. So thank you.
Thank you very much for having me.